To Stimulate or Not to Stimulate by Tim Brocus, Preston Lopez, Stephanie Metz, and me, Quang Pham. In this presentation, we are going to explore whether or not it is effective to stimulate a horizontal or vertical well. We designed an experiment to test that. Hello, I'll be talking to you today about skin, which is very common in the petroleum industry. Skin is created in the reservoir by drilling fluids, completions, and operations. It is located around the wellbore zone, and this is what causes an invasion in the reservoir rock. This is bad. Why is this bad? Because skin unintentionally restricts the flow of our fluid into and out of the wellbore. This is what we call formation damages. Skin can have many factors in how it affects our wellbore. It can reduce the permeability, change the relative permeability, change rock properties, restricts or even stop the flow of our fluid. Now, I'm going to talk to you about different damages. Solid plugging. This is when pore throats are plugged into the rock matrix, which is forced by the mud filtrate. These very small fine particles are dislodged by the filtrate within the matrix of the rock. Clay particles, which is very similar to the migration of fine particles, as you can see here, is a common problem in sandstone, which contains water-sensitive clay. When fresh water filtrates invades the reservoir rock, it will cause the clay to swell or even move, reducing the total pore diameter in the area. Saturation changes. When mud filtrate enters the reservoir, it will cause some changes in the water saturation, and this can cause potential reduction in our production. Sometimes with skin, we will see a higher fluid loss. This will cause water saturation to increase, which results in a decrease in relative permeability. Lastly, I'll speak to you about reverse wettability. All reservoir rocks have water-wet natural properties. While drilling with oil-based mud systems, excess of drilling fluids in the mud filtrate can enter the rock and cause wettability reversal. Now, Preston Lopez is going to speak to you about problems that we face with skin in real-world situations.
Hi, I'm Preston Lopez, and I'll be briefly discussing a few of the steps that industry has taken to overcome skin damages. The use of coiled tubing for overbalanced and underbalanced drilling of vertical and horizontal wells may result in a decline of formation damage in certain conditions. Particular application for coiled tubing drilling occurs in situations where underbalanced drilling is under consideration, as coiled tubing has a few specific advantages with respect to continuous upkeep of more uniform underbalanced bottom hole pressure conditions, as well as the ability to continuously circulate the hull, leading to quicker tripping times and the capability to run an internal water line for less problematic NWD complications. However, there are also a few potential disadvantages associated with coiled tubing, particularly for underbalanced drilling, may be related to reduced hole cleaning ability, as well as greater propensity for potential damage and limited horizontal outreach associated with current coiled tubing technology. The industry has taken to overcome skin damages is carbonate stimulation. The main objective in carbonate stimulation is to create a conductive flow path and bypass the damage. Hydrochloric acid is one of the commonly used products in fracturing and matrix acidizing in carbonate reservoirs. The acid is highly reactive with carbonates, and it is economical, and there is an abundant supply around the world. A great quantity of options are available for acid stimulation techniques, including wellbore cleanup, matrix acidizing, and acid fracturing. Wellbore cleanup is basically exposing the well to acid for a period of time, removing scale, debris, mud, cement filtrate, and anything that can cause skin damage. Matrix acidizing is basically pumping acid at lower pressures than fracture pressure to ensure removal or bypass the damage in pore spaces and improving formation permeability. Acid fracturing is basically pumping acid at high pressure exceeding the minimum fracture pressure, and it will also create long wormholes and channels for communication within the wellbore. Over time, this will erode the filter cake, which is basically causing our skin damage and can lead to better production rates. Industry has shown that matrix acidizing is highly inexpensive, so most exploration and production companies will choose matrix acidizing over the other two.
Hi, I'm Stephanie Metz, and I'm here to talk to you about flow efficiency. Flow efficiency is affected by many factors. One of these factors is whether or not the reservoir is anechotropic or isotropic permeability. Depending on whether or not the direction is all in the same direction or if it is varying in directions can greatly affect your flow efficiency. Because with a skin factor or formation damage, having something in all directions versus in specific directions can greatly affect your production, especially in a horizontal well. Because of the damage and the blockage it causes, you can have a decrease in production, thus having to stimulate the well to either even get a flow at sometimes. Also, the length of the pipe is another factor of flow efficiency. Why not as important in a vertical well because of your reservoir and you're going straight down is greatly affected when you have a horizontal well. Because the longer the pipe, the lower the ratio of formation damage is. Therefore, it is easier to produce, meaning you are less likely to have stimulation issues. But if the damage is severe, even with a very long pipe, you could still have to have stimulation. The size of the skin factor is also very important because in a vertical and horizontal well, if they're roughly the same skin factor, the horizontal well will greatly produce more. Whether if it is severe damage, you will have to stimulate the horizontal well. Also, the quality of the reservoir affects flow efficiency. When a reservoir is very poor, you're more likely to have skin and have formation damage, thus blocking your pipe, decreasing your flow efficiency, where if it is good reservoir, you do not have to generally worry about that. Why formation damage affects horizontal wells more than vertical wells? Vertical wells are usually completed by casing being cemented and are perforated, making it harder for damage to seep in and cause clogging, while in horizontal wells that are usually finished in open hole fashion or with a specific lining that is usually either perforated or has holes in it, causing easier damage to happen. Also, horizontal wells are a lot deeper, making when the skin damage happens, it's harder to be stimulated because it's so deep and getting the acid down there is also more expensive. This causes great flow efficiency problems, and this is why it is better sometimes to do a vertical well instead of a horizontal well, even if you could get more from a horizontal well.
For each experiment, we used a 5-gallon jug with the 13-inch height and a 15-inch diameter. We kept the water level constant and kept the wellbore constant at 6 inches. We used an 8-inch sand pack and a 0.1-inch perforated wellbore for our experiment. For the Reservoir 1, we used a vertical well with no skin, and we calculated the flow rate of 4.45 ounces per minute. For Reservoir 2, we kept everything constant except we added a 0.5-inch skin of a tighter sand. Using this method, we calculated the flow rate of 3.56 ounces per minute. In Reservoir 3, we kept everything constant except created a 6-inch perforated horizontal wellbore for the water to flow through. Using this method, we calculated a Q of 1.38 ounces per minute. In Reservoir 4, just like Reservoir 2, we added a 0.5-inch skin to the wellbore while keeping everything else constant. Using this method, we came up with a flow rate of 0.86 ounces per minute.
Directional well with skin.
When we ran our vertical well test with no skin, we used 3 independent trials, each lasting 5 minutes long, to calculate our flow rate. With the vertical well, we calculated our flow rate at 4.45 ounces per minute. When we applied a skin to the vertical well, we calculated an average flow rate of 3.56 for the 3 trials. With a horizontal well, we used 3 trials as well, each lasting 5 minutes, to calculate a 1.38 ounces per minute flow rate with no skin, and with a skin, an average flow rate of 0.86 ounces per minute. When we compare the reduction between the vertical and horizontal well, we see that the vertical well has a reduction of 20% when the skin is applied, and the horizontal well has a reduction of 38%. when the skin is applied. To summarize our findings, we found that there was a 20% reduction in flow rate in the vertical well and a 38% reduction of flow rate in the horizontal well. This is nearly twice the amount of reduction in the horizontal well as compared to the vertical well. To answer the question we posed in the very beginning of the presentation, it would be more effective to stimulate the horizontal well than the vertical well.
Thank you, and this concludes our presentation.